Assalamu alaikum. Let us start. Still, if some of your friends are yet to join, maybe they will miss 2 to 3 minutes, and we'll need 2 to 3 minutes to start actually. And by the way, the session is being recorded and it will be shared. Don't worry. All right. So in the last class, we started with the state space modeling. And then we saw what is the significance of homogeneous state equation or unforced state variable. We covered these things. Then moving on, we derived this expression, I believe. Up to this, we completed. That is, we have now the Laplace domain expression for del delta and del omega. So we have the two corresponding equations. We know what is del delta 0 and del delta omega. I believe we know. These are our initial states. So why we need these initial states, all of this has been answered in the previous class now. So we'll continue from here. Okay? To have some dynamics in a natural response, all the initial values of the state variables can be non-zero. But the condition is at least one of the initial values of the variables has to be non-zero. So I'm repeating what I just said. So when we are talking about the natural response of a system, then the condition is such that the initial values of all the state variables can be non-zero. Okay, that can be, but the condition is at least one of the state variables has to be zero in its initial state. That is, the initial value of at least one of the state variables has to be zero.
So zero or non-zero?
Sorry. It has to be non-zero, right? At least one of the initial values has to be non-zero. Thank you. Okay, wait, sorry. My Wacom is not working. Just a second. Yeah, it's working now. Okay, so over here we have got two state variables. One is del delta, initial values. Another is del omega, initial value. Both of them can be non-zero, but the condition is at least one of them has to be zero. Okay? So since we are talking about small disturbance and we are talking with respect to the rotor angle, also according to your Hadith Sadat book, what they have assumed is that the initial condition of del delta 0, that is the initial value of this is not 0, whereas the initial value of omega or angular velocity, this is 0. That means this term becomes 0. So if this term becomes 0, now we have the expression of del delta s and del omega s. If I move on to the next page, now you can see that we have the expression of del delta s and del omega s. This is very easy. Okay, how we find out? So how we can find out del delta s? So s plus 2 zeta omega n multiplied by del delta 0. That is what exactly you have on the numerator, and the denominator will be as it is. When you go for del omega 0, what do you have? You will have minus omega n square into del delta 0. That is exactly you have, and the denominator will be exactly as it is. So this is the representation of del delta and del omega in the Laplace domain. To solve the problems, our target is we need to transform this back to our time domain. And for that, what we have to apply? We have to apply the inverse Laplace transform. Okay. So first of all, we applied Laplace transformation. We got the corresponding expressions of del delta s and del omega s. Now again, we have to apply the inverse Laplace transform to get the corresponding time domain expression of del delta and del omega. Then our target will be completed. Okay. So for this purpose, we'll take the help of inverse Laplace table, something that you people are familiar with. There are some tables, okay, from where we get some standard expressions and we get the corresponding inverse Laplace transform, apart from actually applying the formula. So one of the state, we're only interested in one of the states. Okay, don't worry about that. So we are interested in is if we have the form of something like this, that s plus a divided by s plus a square plus b square. If this is the Laplace domain representation, then if you follow the inverse Laplace transform, then can anyone tell me what do we get? Do you remember anyone? I mean, I don't expect you to remember, but still, can anyone recall what do you get? Okay, fine.
So
It will
exponential
be
minus
yes,
80 and
Exponential
cos.
into
Cos.
80, then
cos.
So cos.
Cos.
cos, then
B of
BT.
t.
PT.
very good, very good. Thank you. Right. Yeah, and there is another format that is b divided by s plus a square plus b square, similar type. Again, if you perform the inverse Laplace transform, you will get a similar type of thing, that is e to the power minus 80, but now instead of cos you will get a sine of bt. Very good. Okay, so this is our target. What we will do, you look at the expression of del delta first. So we'll try to see that if we can bring in this particular format, that is s plus a divided by s plus a square plus b square. If we can find this particular expression of this particular format, then from the inverse Laplace transform, we will get the corresponding time domain expression. So we'll go through those some simple mathematics. Okay, these are actually pretty straightforward and very easy. So this expression that we have initially, s plus 2 zeta omega n divided by s square plus 2 zeta omega n s plus omega n square. What are the simplifications that we do? So first of all, we break down our numerator. So we have got s plus zeta n and additional zeta n. So s plus zeta n will give you s plus 2 zeta n. So we are done with the numerator. So if you come to the denominator, you know that we need the format of s plus a square plus b square. Okay. So we'll go with s square plus twice zeta omega ns plus zeta square omega n square and the previous omega n square that we have. So what is the additional term? This is the additional term we brought. So we'll subtract the additional term. The same thing is done on this side as well. Okay. So what happens? You get s plus zeta omega n, no change in the numerator, but the denominator is slightly modified now. So this one, change the color. Okay. So this entire expression will give you is same as a, sorry, not the entire one. Sorry. Yeah, a square plus twice ab plus b square. Yeah. So this will give you a plus b whole square. Then over here, if you take omega n square common, you will get 1 minus zeta square. The same thing is done on this side as well. So what again you have same, there is no change in the numerator. What we have in the denominator, s plus zeta omega n square. Fine. If you take a root over, then you can have a total square. So this is same as, I mean, similar format. So you get s plus a divided by s plus a square plus b square. And this format, if you see, this is same as your b. So what we got, we introduced an additional root over 1 minus zeta square. So that's why we had to divide with 1 minus zeta square. So this entire term is my constant. So I don't have to worry about the constant. If I forget about the constant, what do I have? Over here, I have simply b divided by s plus a square plus b square. So now we can go for inverse Laplace transform. Any confusion over here? I mean, this is very straightforward. Any confusion?
No, sir.
Okay, thank you. So now you apply the formula that we already said. So you apply e to the power minus 80 cos bt plus the constant that we had. The constant remains as it is. Then again, we have e to the power minus 80 sine of bt. Okay. Then again, we go for some simple calculations. Okay, so omega n 1 minus zeta, this entire thing can be written as omega d. So that's what exactly we have done. Similar thing, this entire thing can be written as omega d. Okay, so what we have e to the power minus zeta omega n t. Now we apply. Okay, no, we take common just, yeah. So we take common now. So e to the minus omega n zeta n t, then we have got 1 minus zeta square. So there is an additional 1 minus zeta square root over. So we multiply this root over 1 minus zeta square cos omega dt comes over here. And over here we have got this zeta over here and sine omega dt. Can anyone tell me how we go from here to here? What do we apply? We actually take help of a right angle triangle. Okay, so you draw a triangle with length. Let me change the color. So you draw a triangle with length 1 minus zeta square and the base with just zeta. Then if you apply the Pythagoras theorem, you get your hypotenuse is equal to 1. Do I need to show how you get 1, or you know how we got 1? You know, right?
Yes, sir,
You know, right, how we
Yes,
got
sir.
1?
Yeah, I don't know.
Yeah, very obvious. Thank you. Okay, so if this angle is theta, then you can apply the concept of your basic trigonometry. So your cos theta becomes zeta and your sin theta becomes root over 1 minus zeta square. So instead of zeta over here, you can simply write cos theta. Instead of root over 1 minus zeta square, you can write sin theta. So this is nothing but the formula of sin A plus B. So this is your final expression. So if you know, or if you have the knowledge of theta, then you can easily find this expression. So any confusion over here? Any question?
No, sir.
No, sir.
Now, if you recall your initial lectures, can anyone tell me what was delta equal to when we applied the concept of linearization? What was delta written equal to?
Delta naught plus del delta.
Right, delta naught plus del delta, right? So this is your that del delta. Okay, so your final expression. Oh, still sorry, we are still left with del omega. Sorry, I skipped one line actually. Yeah. So now this was the expression for your del delta. We are still left with del omega. So this is your expression for del omega. Actually, del omega is much more easier. Okay. So you simply take root over 1 minus zeta square over here and you divide with 1 minus zeta square. The denominator operation is same as the previous one. So this is nothing but a constant. And this takes the form of b divided by s plus a square plus b square. Okay. You apply the inverse Laplace transform and you finally end up getting this formula. So again, so I believe this should be very simple. So now, as I was saying, if you recall, your delta t was del delta 0 plus del delta t. So this is the expression for your del delta t. So over here, instead of del delta t, you simply plug in this value. So if you plug in this value, you end up getting this expression. The same logic goes for omega t as well. So omega t, there is a minus sign because your final expression, as you can see, del omega, there is a negative sign. So you get a minus in between. So this is your final expression that we were targeting. And this was the main reason why we learned about state space modeling and all those things. So any question until now? Okay. So if there are no questions, some small things to discuss over here. That is, this is known as zero state response. Can anyone tell me why this is known as zero input? Sorry, not state, zero input response. So can anyone tell me why it is known as zero input response? Why is it known as zero input response? Anyone?
So this is a steady state response. That's why.
No. Come on. This was discussed in detail in the last class. Why is it known as a zero input response?
So we're getting output without giving any input.
Okay, yeah, right. The main thing is we are not giving any input. Okay, for this I have to get back over here. So if you recall, why we incorporated this term? Because we had no input, right? Again, if I go back, see, your default format is ax plus bu. But since we don't have any input, we have neglected this term. That is, there is no input. Since there is no input, we took the initial condition. So as we do not have any input, this is known as our zero input response. Okay. Don't worry about this math. We'll take the math in the next class. Okay. Not in this class. Okay. So if what can be the other scenario? I mean, this is zero input response. So what will happen if you give some response? I mean, if there is some input. Okay, so that is the topic we'll take next, and we'll finish this class very quickly. Okay, before that, until this, do you have any problem? Because today's class was mostly simple mathematics, so that's why I mean, what? I went a little fast. So any confusion, anyone?
No, sir.
All right. So if there are no confusion, then let's keep on going. So now we'll see what happens when we go for forced response. So all of you should recall this expression. This was from your previous slide. What was the difference? Can anyone tell me what is the difference with this expression and the expression that we had considered so far? What is the difference?
The del P input.
Right. Previously over here we had a zero. That is, we had no input. Now we are assuming that let us try and increase the input by a very small amount of delta PM. So this is nothing but my U, that is my input. So now we'll see what happens if we have this format. Okay. So again, as you know from your previous class, your d square del delta by dt squared, the coefficient has to be 1. So you divide the entire expression with h by pi f naught. So on the right hand side, you have got pi f naught by h. So this entire thing can be taken as my input. Okay. So let us assume that this is our input delta u. This is your standard second order system when you have got an input. So d square del delta by dt square twice zeta omega n d del delta by dt omega n square. These are all same as before. So again, like before, can anyone tell me what will be my x1 and what will be my x2 from the concept of state space representation? What will be your x1?
d delta by dt.
That will okay, fine. That will be x1 dot. Fine, yeah. D del delta by dt. Therefore, my x1 will be simply del delta. What about x2? Or let's keep it. What will be x2 dot?
D square.
D, D square D
D square del delta by dt square, which is same as my
d beta del delta.
same as what? This can be
D
written as
delta.
in terms. So your x2 is actually nothing but x1 dot,
X1
right?
dot.
We know these things, isn't it? We can understand, relate these things. Okay. So exactly the same thing has been done, as you can see. So x1 is your del delta, x2 is your x1 dot, that is del delta dot, that is d del delta by dt, that is your del omega. So if you go back, so over here, what do you have? Over here, this is nothing but your x2 dot, right? So if this is your x2 dot, you have del u minus twice zeta omega n x1 plus omega n squared del delta, or you can write simply, okay, this one will be x1 dot, I think, and x1 dot is same as x2. Okay, so this is exactly what you have, as you can see over here, minus omega n x1 minus 2 zeta omega n x2 plus del u. Any confusion up to this? It is clear, right?
Yes, sir.
Yes, sir.
So now if you go for your status space representation, you have got x1, which is nothing. I mean, x1 dot is simply equal to your x2. So 0 and 1, which is equal to your x2. And x2 dot is minus omega n square into x1 minus 2 zeta n into x2. Now you have got an input. So I have got the matrix B, which is 0, 1, and del u is nothing but our input. So if you go, now you have the format of x dot is equal to ax plus b del u. Okay. Now this is known as your forced state variable equation or zero state equation. By the way, it is known as zero state equation because the initial values of your state variables, are now 0. Okay. Because since I now have an input, I no longer require the initial values of the state variables. So since the initial values of the state variables are 0, this is also known as my zero state equation. And the output, as you can see, both my x1 and x2 are considered as outputs. So a simple expression. So if I go, if this is your x dot is equal to ax plus b del u, if you do Laplace transformation, can you tell me what will you get? If you do the Laplace transform of this one, what will you get?
S XS
S x s.
A X of
Will
S.
there be a minus x0?
No, sir.
No,
Because we
sir.
are considering zero state
Then
equation.
this will be equal to a, then
X of S.
x of s, then okay, fine. Then it will be b. It will be del u by s. There has to be a reason why it has to be del u by s, because we were assuming that this is nothing but a step input. So if we have got a step input, the Laplace transformation is del u by s. Okay. So we'll assume that this is nothing but a simple step input. So that is exactly as you can see, it is done over here. So sxx plus axs plus b del u, and you can see that del u is nothing but del u by s. Why? Because we have assumed this to be an step input. Then the rest of the things should be pretty clear. So you change sides, you take SI inverse, sorry, SI minus A inverse. We already saw how we get this matrix, okay? So we get this matrix. So finally you have got the expression of XS. So what do you have inside XS? XS is nothing but this is del delta S and del omega S. So if you find out the expression, so del delta S will be this one multiplied by 0 plus 1 into del U. This del U comes over here, this S comes over here, and in the denominator will be this one. Similarly, if you go for del omega, so minus omega n square multiplied by 0, so that is 0. S multiplied by 1, so there has to be an S in the numerator, multiplied by del U by S, so multiplied by del U into S, so this S gets cancelled out, that's why it is not shown, and you have got the denominator over here. Any question? Any question until now?
No, sir.
Thank you. So now again, as before, you have got the S domain or the Laplace domain representation of both del del and del omega. Now you have to go for inverse Laplace transform. Okay, so this thing I'll go a little fast. So now instead of applying all those transformation, we went for partial fraction. Okay, something that you have covered in your intermetric level probably. So you go for partial fraction, and you can see that this is similar to which term, which format. This is not a new format actually. Okay, again, this is not that straightforward. Okay, you need the concept of the triangle as well. So you need theta, you need the concept of the triangle. So either way, so you have got del u by omega n square, so 1 divided by s. So if you take the inverse Laplace transform, that is your step input, that is 1. So you get del u by omega n square, and this one, if you apply the inverse Laplace transform, you will end getting up this. You can try it, okay? Try it at your home. It will be almost similar to the previous one, okay? Maybe it will take you 5 to 6 minutes to find out how we got all these things. Similarly, if you go for the next one, del omega, so this is the expression for your del omega. It is same as before. You insert root over 1 minus zeta square, root over 1 minus zeta square. So this is your constant. So this constant comes over here. And this, I believe, okay, this one is better over here. So this takes the form of b divided by s plus a square plus b square, I guess. So you apply. So the constant comes over here. So del u, omega n 1 minus zeta square e to the power minus at into sine of bt. So this can be written as omega d. So you find out, end up getting this expression. So now these are your final expression for your forced response, that is del 0 plus del del t, and for del del t you get these expressions, and this is known as your zero state response, which I already explained why it is known as zero state. Any question up to this? We'll solve math in the next class. So up to this, if you have any question.
No, sir.
Fine. Okay, so as I said, so today's class is actually very small. If I had taken it physically, maybe instead of showing you the equations directly, I would have solved one by one in the board. That would have been more interactive, but solving one by one over here, it does not make sense. So that's why I just showed you all the expressions. The explanations were pretty simple and straightforward. So with this, this slide also comes to an end. Okay, so this is the end of your small disturbance stability probably. Yeah, we have two mathematical examples to solve, that is 11.2 and 11.3 of our Hadith Adat book. So we'll take it in the next class probably maybe on next Friday. So I will request every one of you to try and attend the class on Friday, that is this coming Friday, because I will discuss about your assignment 3, or assignment 1 equivalent to quiz 3. So I will discuss how you can solve it. So I will request all of you. Of course, your attendance is optional throughout the month of Ramadan, but still I will request you that if it is possible, try to attend the class of next Friday. Okay. Then if we have time during the class also, we'll solve example 11.2 and 11.3. So any question from your side?
Sir, I
Any
have a
question?
question from previous class.
Okay, wait. Let me share again. Okay, previous class. Okay, tell me which slide number should I go to?
Sir, RLC সার্কিট যেটা ছিল ওটাতে।
Here?
জি স্যার। স্যার এখানে x1 আর x2 আমরা I আর VC কেন ধরতেছি? মানে আমরা তো VL বা VR ও ধরতে পারতাম।
X1 and X2. No, acha, I got it. I got your question. So you are saying that what if we consider? So you're saying that we could have considered that X1 is equal to VL or X2 is equal to VR, something like this?
জি স্যার, স্যার এভাবে ধরলে তো আমরা মানে পুরোটা হচ্ছে ইকুয়েশনটা ওইভাবে চেঞ্জ করতে পারতাম।
So if you consider X1 to be VL, then you need a format like this, dVL by dt. Can you bring this format for this expression? And if you take X2 as VR, then you need the format of dVR by dt. You have to have the dt format associated with X, right?
ইয়েস স্যার।
So is it possible to get dVL by dt and dVR by dt for this circuit? Is it possible?
মেবি নট স্যার।
It is not possible. You cannot have dVR by dt. Okay, it's not possible. So the condition for your x1 and x2, that is for your state variable, is that they must be in d by dt format. Must. So you see the only two variables which are in d by dt format are your current and your capacitor voltage. So that's why we have chosen x1 and x2 to be I and VC respectively. Is it okay?
ওকে স্যার।
Understood? Okay. Any other question, anyone? Any question?
Sir, I wanted to ask something else.
Something else, not related to today's or yesterday last class topic?
No, sir, not related to classes. Sir. Sir, it's like, sir, when can we see the script of quiz 2, sir?
When can you see the script of?
Quiz 2, quiz 2.
Oh, quiz 2. Again,
Second quiz, yes, sir.
yeah. So for this, you have to talk to Maria, okay? She is in charge of all your quizzes. That is quiz 1, quiz 2, assignment, as well as your quiz 4. So Sears trying to contact with her. Today also one of your friends came to my room to see the script of quiz 2. I don't have the scripts actually, okay? So talk to her, and I mean, after talking to her, still if you have some queries, then you may come to me. But I don't know how much helpful I can be, because this is a hard department now, okay? That is dealing with the quizzes. But still, I can try and help. Is it okay?
Yes, sir. Yes, sir.
Anyone else with any other confusion? Okay, let me stop sharing the stop recording.
Sir, I wanted to ask something else regarding any